Hello dear students, welcome to Pen and Paper Chemistry on YouTube. Students, welcome to part 13 of the topic Thermodynamics. Enthalpy of atomization, lattice enthalpy, solvation enthalpy and enthalpy of solution. These are the terms which we had spoken about under the heading Born-Haber cycle, and there I had mentioned that we will take them up as a separate heading so as to not confuse between the various definitions, especially the lattice enthalpy. Enthalpy of atomization. For this, let's first guess what do you mean by atomization. Any guesses? Yes? Okay, you can say the answer in your mind. That will make the learning more interactive and you will not feel bored. So atomization is formation of atoms. So when you are talking about the enthalpy change, when 1 mole of atoms are formed, and in what form are they formed? In the gaseous state, from its elements in their standard state. Whatever enthalpy change takes place in the formation of 1 mole of atoms in the gaseous state from the elements in the standard state is what we call as enthalpy of atomization. So if you notice over here, the terms to be stressed here, 1 mole of atoms, gaseous state and formed from the elements in the standard state. For example, oxygen, the standard state is gaseous form. This breaks down to give you 2 oxygen atoms in gaseous form. We know that the bond enthalpy for oxygen, the standard bond enthalpy for oxygen is 498 kilojoule per mole. Now this is the enthalpy change if you notice when 2 mole atoms of oxygen are formed. If we want to derive the enthalpy of atomization, that means the enthalpy change when we are talking about the formation of, yes, 1 mole atom. So what will you do in order to derive the enthalpy of atomization from bond enthalpy? Yes, we will divide the whole equation by 2. So that will give me the enthalpy change when 1 mole atoms of oxygen are formed, and that gives us a value of 249 kilojoule per mole. Working on the same lines, can you calculate the enthalpy of atomization of hydrogen? See, it is again a diatomic molecule. The standard molar bond enthalpy of hydrogen is given as 434 kilojoule per mole. So what will be the enthalpy of atomization of hydrogen? Pause the video please and calculate. So we have divided by 2, 434 divided by 2, you get 2 times 2, 2 times 1, 2 times 7. So we have 217 kilojoule per mole. Take the third case. Sodium, standard state solid, changes to sodium gaseous state. Now here it's an atomic state only. We know that the standard molar enthalpy of sublimation, because it's the direct process wherein sodium solid is changing to sodium gaseous. This is 107 kilojoule per mole. So how will you calculate the enthalpy of atomization for sodium? Will you divide by 2, 3 or what? Yes, it will be the same 107 kilojoule per mole, because here we are talking about 1 mole only. We don't have to divide by 2. So you just use a bit of logic and you will be able to find your way around this. Coming to lattice enthalpy, solvation enthalpy, enthalpy of solution. Now these are a bit confusing when you read too many reference books, too many textbooks. Somewhere you'll have lattice enthalpy, lattice dissociation enthalpy, enthalpy of crystallization. So just concentrate on what we're going to discuss over here. And then still if you have doubts, please post your doubts in the comments. First of all, what is lattice? Lattice is nothing but 3-dimensional ordered arrangement of particles. We know that in a crystal of sodium chloride, we have sodium ions surrounded by chloride ions. The chloride ions in turn are surrounded by sodium ions and they are held together closely due to electrostatic forces of attraction. Now, if I want to break this lattice, I will have to give it some energy. I will have to apply some form of energy. And that energy or the heat that we have to give is what we will term it as lattice enthalpy. What is lattice enthalpy? The enthalpy change when 1 mole of a solid ionic compound is converted into its individual gaseous ions so that they are infinite distance apart from each other. Basically, they can't come close to each other. You pull them away so much that they can't reunite to give you back the crystal. Now, the confusion over here is in many of the books, you will find the term lattice dissociation enthalpy and lattice formation enthalpy as two different terms. Just reverse the definition. That means when 1 mole of solid ionic compound is formed from its individual gaseous ions which are infinite distance apart from each other, that enthalpy change is known as the lattice formation enthalpy. The term that we have described over here is actually lattice dissociation enthalpy, but most of the texts, most of the literature talks only about lattice enthalpy. You just have to see the change which is being mentioned in the form of the equation over there. The reverse process is actually lattice formation enthalpy. In some places, you will also find the term enthalpy of crystallization as well over here. Please do not get confused. So when we are dissolving sodium chloride in water, first step is the sodium and chloride ions are drawn away from each other by imparting it energy, and that is called lattice enthalpy. Now these sodium and chloride ions, they can't exist independently. I'm dissolving them in water. Water, we know, is a polar solvent. We know that this has a negative N. With the result, what will happen is this will align. So for the sake of simplicity, I've taken the water molecule as negative and positive. It's a polar molecule. You can also have a polar solvent over here. Sodium ions and chloride ions have got separated. The next step is the surrounding of these sodium ions by the water molecules with their oppositely charged polar end facing each other. Now let me put it in simple terms. Sodium is positively charged. The negative end of the water molecule, it gets attracted towards the positive sodium ion. Here, similarly, there will be a number of water molecules surrounding the sodium ion. Same way come to chloride ion, which has been formed in the gaseous state. Chloride ion is negatively charged. It will be attracted by the positive end of the water molecule. So if you notice over here, sodium ion, we have the negative end of the water molecule, whereas for chloride ion, we have the positive end of the water molecule facing it. This process is what we call as hydration if your solvent is water. If it is some other polar solvent, then it will be called as solvation. So solvation enthalpy or hydration enthalpy, they are similar terms. Hydration word is specifically used if your solvent is water, as we have taken in this case. So going back to where we started, sodium chloride first breaks down to form sodium ions in the gaseous state, chloride ions in the gaseous state. The enthalpy change involved over here is called lattice enthalpy. Sodium ions and chloride ions get hydrated or solvated. The enthalpy change is called as hydration enthalpy. Now, since the oppositely charged ions, they are coming close to each other, there is attraction. Attraction means there will be release of energy. So that is why we put delta H as negative. Enthalpy of solution. That's the next definition. The whole process results in the formation of solvated ions of sodium and chloride. Basically, sodium chloride has got dissolved in water and we wait till the enthalpy stabilizes. So, enthalpy change when 1 mole of ionic substance dissolves in a solvent to form an infinitely dilute solution. Why are we talking about an infinitely dilute solution? Means that when more water is added to it, there is no change in enthalpy. That is the stage we have to bring this solution to. Now, this enthalpy of solution involves the two enthalpies, the lattice enthalpy and the hydration enthalpy. Hence, our enthalpy of solution is nothing but the culmination of lattice enthalpy and solvation enthalpy. Whether our solution will be endothermic or exothermic, that means whether on dissolving a salt in water, the test tube becomes cold or the test tube becomes hot will depend on the enthalpy of solution. If your enthalpy of solution is positive, that means it's an endothermic process. In other words, heat is being absorbed over here, right? The amount of heat absorbed is more than the amount of heat given out. Then your test tube will become cooler. That means it's an endothermic process. On the other hand, if your test tube becomes heated, that means the enthalpy of solution is negative. Heat is being generated when you are dissolving. For example, when you add acids to water, you will find the test tube becomes a little warm. When you do these experiments in the laboratory, you will find that your test tube becomes, whereas when you dissolve the nitrate salts in water, you will find that the test tube becomes a bit cooler than what it was initially. The only difference over here is the enthalpy of the solution, which again is dependent on the lattice enthalpy and solvation enthalpy. I hope this makes the things a bit more clearer. If you like, please subscribe to the channel. Learning chemistry is fun. This is not sufficient in the sense the YouTube video is okay if you want to understand. But if you want as a backup, I have loaded all this material in the form of written notes on the Google site Pen and Paper Chemistry. You can download and keep it for your reference in the future in case any confusion arises. Please don't forget to share this channel with your friends if you like it. Happy studying to all of you. The only mission of this channel is to make learning chemistry easy and fun for all you students. With the help of the periodic table, the flowcharts, the graphs, diagrams, dealing with numericals, how to deal with numericals. And this can only happen when you keep a pen and notebook ready so that you can also take down notes for offline reference. There is no subscription to join the channel. There is no payment at all. Only request is to help spread a word about the channel by sharing it with friends, classmates, juniors, seniors, so that chemistry can be easy and fun for one and all. See you in the next video.